in the 6 bottles activity, you're going to see lots of precipitation reactions. So a precipitate is a solid formed from 2 solutions. So we have 2 solutions react and form a solid. And that solid is called a precipitate. The reaction is called a precipitation reaction. So you are going to be given the identities of 2 reactants, both of which are aqueous solutions. Your job is to do 2 things. It's going to take a lot of steps to do those 2 things. One is to write a balanced chemical equation. So you need to figure out the products and then balance the chemical equation. And then the other thing you're going to do is to write a net ionic equation. And I'll talk about what that is. Hopefully you know from last week from reading, but I'll talk about what that is when I get to that step in the example. On the screen, I have them color-coded because I'm going to try and color-code my work to match the steps that I'm doing, since there's so much stuff going on here. Okay, so here is my example. Because you're going to be doing this for your lab assignment, I also included observations for my example. Both of the reactants are clear, colorless solutions. To me, clear and colorless mean 2 different things, where clear means that it's see-through or transparent, and colorless is a lack of color. So my first step down here is to determine the identity and the charge of each ion. So we're doing that for the reactants. By identity, I mean, is this an individual ion? Is this a polyatomic ion? That's what I mean by identity. Where does this break into 2 ions? In this case, it's the sodium is 1 ion and the sulfate is a different ion. And then the charge, that's going to be using the periodic table or using your list of polyatomic ions. So I'm just going to write this down. Sodium is my first ion. I can go to the periodic table, see it's in group 1, and it gets a +1 charge when it's an ion. And then sulfate is the other ion. I can go to the list of polyatomic ions and get the charge for that. Right now, I am ignoring that there are 2 sodium ions, because right now I am only dealing with the identity and the charge. I'm going to deal with the number later. I'm going to deal with how many there are later. Right now for step 1, I'm only identifying them and figuring out the charge. I'm going to do that for my other substance too. Now silver is in the middle of the periodic table. So that might be one that you don't know. And that's okay. You can always figure out the positive one if you start with the negative one. So here I have nitrate. That's a polyatomic ion. You can look that up on your list. And that has a -1 charge. So now I look and I see I have 1 of the nitrate ions in my formula. I have 1 of the silver ions in my formula. If the nitrate is -1 and there's 1 of each, then the silver must be +1. So I've done the first step and figured out the identity and charge of each ion. So I'm going to move on to step number 2, and that is to follow the double replacement format. Remember that the format for double replacement is that the ions in 2 ionic compounds switch partners. So the positive ion from 1 pairs up with the negative ion from the other. There's only 1 new combination that they can make, because you can't put 2 positives together and you can't put 2 negatives together. You have to put a positive with a negative, and we're looking for a new combination, not the ones that they're already with. So the positive has to go with the negative from the other compound. So that's step 2. Just figure out who the new partners are. In step 3, this one is the one that has common errors for students. So I'm going to put some stars there. I'm going to underline, use the charges. Maybe I'll highlight, don't balance yet. And you're going to determine the formulas for the products. Another thing I want to point out is that I am writing my work sort of down below. This is not where my answer is going to go. My answer is going to be the balanced chemical equation up here. So I'm doing my work off to the side or down below somewhere else. Okay, so for the sodium and the nitrate, I have an Na plus and an NO3 minus. I'm going to think, how many of each of those do I need to make 0? Well, I have a +1 and a -1. Just one of each makes 0. So that's going to be NaNO3. Here's the part that throws people off. Earlier, I had Na2. I am not using that 2 here. And that's because earlier, sodium was with something with a +2 charge. When sodium is with something, sorry, it was with a -2. Earlier, sodium was with something with a -2 charge. When sodium is with something with a -2 charge, you need 2 of them. But now sodium has a new partner. This partner is only -1, so you don't need 2 of them. 2 would be too many. You only need 1 of them. We're going to do the same thing for the silver and the sulfate. Remember, when you write these formulas, you always put the positive ion first. So I have a silver with a +1 and sulfate with a -2. So I'm going to think about how many of each I need. +1 and -2 do not work out. So I'm going to say I need more of the silvers in order to get 0. So that's going to be Ag2SO4. I didn't have 2 silvers initially. That's because it was with something with a -1 charge. Now when it's with something with a -2, you need more of them. So it might bother you that the equation is not balanced. That's okay. We're going to get to it down here in step 5. Just because we haven't done it yet doesn't mean we're not going to do it ever. We will do it. But for right now, I'm just filling in the formulas for the compounds. And I'm leaving some space. I'm going to leave some space to balance. I'm going to leave some space to fill in the phase labels. So right now I'm just filling stuff in spread out. So that was step 3. My goal was to determine the formulas for the products. And I did that by using the charges. I am not going to balance yet. That's going to come in a later step. All right, next, I'm going to use the solubility rules to determine the phase labels. So I'm going to pull out the solubility rules, and I'm going to look up the 2 compounds that we just figured out for the products. One of them is NaNO3. So we're going to go to the solubility rules. Remember, we start on the left, and we try to find one of the ions that is in our compound. So we're going to look for either sodium or nitrate. Doesn't matter which one. In this case, they're both listed. So I happen to see nitrate first. I see that nitrate is in the soluble section, but I'm going to check for exceptions. Nitrate has no exceptions. So all compounds containing nitrate ions are soluble. Because this is soluble, I'm going to write AQ. AQ is for aqueous. It means dissolved in water. We do have water. Both of my reactants were dissolved in water, so there is water present. And so my sodium nitrate is going to be aqueous. I'm going to do the same thing for the silver sulfate. So we're going to do the same thing for this one. We'll go back to the solubility rules. And we're going to look up either silver or sulfate on the left side. Silver is not located on the left, so we need to use the sulfate. Make sure you pay attention to sulfate versus sulfide. You'll get different answers if you, well, in this case, you'd get the same answer. But it's a good thing to watch out for. So this is SO4, sulfate. And we see that it is in the section marked soluble. However, we check for exceptions, and silver is an exception. We have silver sulfate. So that is going to be insoluble. Insoluble means does not dissolve in water. And since it does not dissolve, it's going to exist as a solid. So, ionic compounds have very strong bonds. So they're going to be solids at room temperature unless they dissolve in water. So this is going to be a solid. Okay, so that was step 4, use the solubility rules to determine the phase labels. The last thing to do for the first part of the example, for the first answer, is to balance. So now we are going to fix the fact that we have 2 sodiums on the left and only have 1 on the right. We're going to deal with that just the way we've been doing when we balance equations and put a big 2 in front of the sodium nitrate. So that balances the sodiums. It unbalances the nitrates. So this 2 applies to everything that comes after it. So I have 2 nitrates on the product side. I need to have 2 nitrates on the reactant side. So I'll put a 2 here. That affects the silver, but that's good because I have 2 silvers here and I already had 2 silvers on the product side. Just in case, we can check the sulfate, 1 sulfate ion on the reactants, 1 sulfate ion on the products. This is now balanced. So this is the first answer. I'm doing 2 things. I am writing the balanced chemical equation, that's this, and I'm also going to write the net ionic equation, which I'll do with steps 6 and 7 in my set of steps. What I wanted to point out before we go on is that this answer does not have the charges written. Even though these are ionic compounds, even though this actually exists as ions in solution, we don't write it that way. When we write the balanced chemical equation, when we write formulas for compounds, we do not write the charges, even if they are actually there. So that's why I did my work down below. There is room for you to do the work down below. Leave this space for your answer. The other thing to do is to write the net ionic equation. I'm going to do that in 2 steps. The first step that I'm going to do is actually to write the complete ionic equation. Now, this does take more work, but it has 2 benefits. The first benefit is it shows how things actually exist. And so that's nice to see. It's very, very real, very honest. The second benefit is that it is a helpful step on the way to getting the net ionic equation, which is what I want as your answer. The way that you do this, so this is how you get the complete ionic equation. You are going to separate aqueous compounds into their ions. So you're going to rewrite any aqueous compounds as separate ions, keeping track of the numbers as you do so. So I'm going to take anything that's aqueous in my balanced chemical equation and rewrite it as ions. And I'm going to think about this, how this actually exists. So this compound actually exists as 2 separate sodium ions and a sulfate ion. The 2 sodium ions do not stay together because they are both positive. So I'm going to write this as 2 Na plus Aq. When a 2 is written out front, that means you have 2 separate examples, 2 separate ions here. Rather than when we write a subscript, that means that the things are attached. And then I have a sulfate ion. So I took a compound that was aqueous and I rewrote it how it actually exists. 2 sodium ions and a sulfate ion. I have in the past seen students write Na plus plus Na plus plus sulfate. That's fine. It takes more writing. You might not be able to fit it all in one line, but if that makes more sense to you than putting the 2 out front, then that's fine. Next, I have 2 copies of silver nitrate. So because I have 2 copies, I'm going to get 2 silver ions, and I'm going to get 2 nitrate ions. Remember that a 2 out front applies to everything that comes after it. So 2 copies of silver nitrate give me 2 silver ions and 2 nitrate ions. Next, I'll move along to the products. My first product, I have 2 sodium nitrates, that is aqueous. So that's going to give me 2 sodium ions and 2 nitrate ions. Now remember what we were doing. We are only breaking apart aqueous compounds. The last compound that I have is a solid. So I'm just going to copy that as is. So I'm not going to change that, just going to copy it down. I only break apart the things that are aqueous. So that is the complete ionic equation. Like I said, it's good for showing you how things actually exist. Before the reaction happens, I have all these separate ions floating around. They're separated by water. They are not touching each other. After the reaction happens, some of the ions are still just floating around. Some have found each other and formed a solid. That solid will start as cloudiness, and if you let it sit, it'll sink to the bottom. Okay, but our goal here was actually to get the net ionic equation. So what we're going to do that is cross out the spectator ions. Spectator ions are ions that are the same on both sides. What I mean by that is they are ions that are exactly the same in the reactants and the products. They did not change. They're called spectators because they did not participate in the reaction. They were there and they watched, but they didn't do anything. So that's what we're going to look for. We're looking for things that are exactly the same on both sides, and we're going to cross them out of cross them out of the complete ionic equation. Sodium ions are exactly the same on both sides. Nitrate ions are also exactly the same on both sides. The other 2 ions change. They start out as separate aqueous ions. They end up together as a solid. So that does not count as exactly the same. That counts as different. And what we're going to do is copy down what's left. What remains is our net ionic equation. So I'm going to copy down the things that changed, the things that were not exactly the same on both sides. If you kept track of the numbers as you went along, you should still have a balanced equation now. So I have 1 sulfate and 2 silver ions create Ag2SO4. So that is the other answer. In your lab this week, I will be looking for 2 answers. The balanced chemical equation, that's the one that I circled, well, boxed in black up above. That's what we did with steps 1 through 5. And then I also want the net ionic equation. You may show me the complete ionic equation as work. I sort of recommend that you do that for the first couple. And then if you feel comfortable not writing the complete ionic equation, then you can. But what I'm going to be grading are this and this. So you're going to do that in the 6 bottles lab.